So welcome to another homework video that we're going to begin. This is homework on page 57, the following numbers right here, and let's begin. Number 17 is saying a Hamiltonian path in a graph is a tour of the vertices of the graph that visits each vertex once and only once, and starts and ends at different vertices. So the difference between a Hamilton circuit and a Hamilton path is that we're not going to make a circuit out of this. So for each of the graphs in exercise 13, does the graph have a Hamiltonian path? Well, here's the graph from 13A, and I'm wondering if we can find a Hamilton path. Well, of course we can. We need those two edges because that's that's valence 2. This is valence 2, so those edges will have to be part of it, and these edges too. The difference is that I don't have to finish here, so I'm going to be all right there. If I start here, I can go here, around there, and here, connecting things, and I can just end there, which is a perfectly fine Hamiltonian path. In part B, still part A, 13B had a graph like this. I need a Hamiltonian path. Our problem with a circuit was if I go down here, covering all these vertices, and then come back up here, then when I come over, I can go down, but I cannot make it back to where I started. But a Hamilton path will do just fine. I can come down, finish all the stuff in the middle there, come across, kind of back up the same way, and then go across, come down here, hitting every vertex, and we have a Hamilton path which started here and ended there. I'm sure that there are other solutions to both of these problems, but those are possible solutions. Then 17b asks, does each of these graphs have a Hamilton path that starts at x1 and ends at x2? Well, here's the graph from 13a. That's vertex x1 and this is vertex x2. So I would have to start here and end there. We're going to run into trouble with this vertex there. So, yeah, the real problem is that with these three vertices, I have to be able to either start or end, really, at one of these, which, as you can see up here, is what I did. I ended here. This was our problem vertex with the Hamilton circuit, so I also need, anyway. So can I start here and end there? I think by inspection you'll be fairly convinced that you cannot. From here I can go around there and get that. I can come over, or I could try to get this. There's no way I can get and cover those vertices and get here. Oh, whoops, I'm not on the video. I can start here and come around there, come over, but there's no way I can get both of these vertices. I can't get that and then come back. There's nothing I can do. So this one, there is no Hamilton path that starts at x1 and ends at x2. This one down here, I want to start at x1 and end at x2. Well, I would have to be able to, I can't come over here, or else I've used x2 already. So I would have to come down, and then if I go over this way, there's no way, I can't come up here and use those because then I have to revisit this. So going up here is not possible, and if I go over here, there's no way I can end at x2 because I would have to catch these somehow. So there's no way I can start at x1 and end at x2. That is also not possible. Part C, this keeps moving. Part C, describe 3 real-world situations where finding a Hamilton path in a graph would be required. Well, it's still the idea that I need to visit every location, but it's fine for me to start at one place and end at another place. So there would be similar types of applications, except that we don't care about returning to where we started. So maybe this is, picking up friends, and driving them to school. In this case, you have to make it to all of your friends' house, so you have to visit every vertex in this case, but you're going to end at school where you started at your house. So that would be a Hamilton path, not a Hamilton circuit. It said 3 real-world situations. So another one might be a cop responding to calls, who then takes his car home at night. And this assuming that he picked up his car at the station and then takes his car home, or maybe he took his car home last night and now he's going to park it at the station tonight. This is annoying. So that would be a second one. And anything is going to be allegorical to this. If you have any other situation, I would probably just go to another service worker, any other service worker who ends up starting and ending at different places. So, I don't know, a meter maid who has to visit different locations, a ambulance driver who starts and ends at different ambulances, things like that. Or at different hospitals, I mean, things like that. So there's problem 17. Number 18. Using the terminology of exercise 17, draw a graph that has a Hamilton path but no Hamilton circuit. So, the easiest thing I can think of is if I draw two vertices and connect them, I can go across this thing. There's no way I can come back. So there's a Hamilton path, there's no Hamilton circuit. 18b, we want an Euler circuit but no Hamiltonian path. Well, an Euler circuit tells me everything has to have valence 2, so I have to do like, I don't know, things like that, and I can't have a Hamilton path. Well, I have to be able to go out and come back, which means no matter what I do, I can go out and touch every vertex. So I propose that B is not possible. The book, the curriculum, in their solution key, presented this. They said this graph has no Hamilton path, but I propose that they're wrong because I can go around this way, and right there is a Hamilton path. Yeah. C. We need to be able to come up with something that has a Hamiltonian path but no Euler circuit. I would go back to exactly what I drew in part A. Two vertices and I connect them. There's my Hamilton path, but I have no Euler circuit. Good. Problem number 19. Okay. To practice concepts of Euler circuits and Hamilton circuits, determine which ones of the following, whether there is an Euler circuit and or a Hamilton circuit. And if there is, write it down. So in A, first of all, I'm going to look for Euler circuits because they're easy. So an Euler circuit is all about even valences and connectedness. This graph is connected. X1 has valence 4, so does X2, X8, and X7. X3 has 1, 2, 3, 4, and so does X4, X6, and X5. So I know that there is an Euler circuit. So 19A, I will write down my Euler circuit. In order to do an Euler circuit for A, I'm just going to start at that top left corner, X1, and I'm going to go in and finish this triangle, and then I'll go to the next one. Go in, finish the triangle, go to the next one. Go in, finish the triangle, go to the next one. That's going to be my plan. So that is X1, X3, X4, X1, then X2, X4, X6, X2, then X8, X6, X5, X8, and then lastly I'll go to X7, X5, X3, X7, X3, X5, X7, and then back to X1 where I started to finish that Euler circuit. Let's go ahead and look for a Hamilton circuit in there while I'm on part A. So, a Hamilton circuit, I just have to touch every vertex. I would think X1, I'm just going to go in, finish those vertices, go down, finish these vertices, and then go back. You could also go in, go all the way around here, go back out, and go all the way around. I'm sure there are other ones as well. I'll just go X1, X3, X4, X2. So I've done this. Now I'm going to go down to X8, X6, X5, X7, and back to X1. X8, X5, X6, X5, X7, X1. Oh, And there would be one Hamilton circuit possibility for that graph. Good. Part B. And I guess I'll scoot down. Part B, we'll start there. Part B, first I'm going to look for an Euler circuit. Euler circuit, it's all about even valences and connectedness. This graph is connected, valence 4, valence 4, valence 4. Inside here I have valence 4, valence 4, and valence 4. So there should be an Euler circuit. For an Euler circuit, I'll go, let me think, around, I'll come back here, go down, kill this piece, go up, around there, around here, down, and then back up there, I think works. So my Euler circuit, this is annoying, for part B, I'm starting y1, y2, y3, y1. So I've done those. Then I'm going to go y4, y3, 4, 3, y5, y2. So I've gone around, come back, kind of squiggled across there. Then y6. I've made it to y2 to y6, y5, y4, y6. And then back to y1. For a Hamilton circuit, I think the easiest way to do a Hamilton circuit in B is just going to be to go around that big triangle. So y1, y3, y2, y5, y6, y4, y1. y4, y1. Should be a good Hamilton circuit just going around the edges. Part C. First I'm looking for an Euler circuit. Z1 has valence 3. There's no Euler circuit. Part C. No Euler circuit. Hamilton circuit. I just need to touch the vertices. From here I'm going to go in, go around that triangle, down, up, go around the square, down, up, in here to the triangle, up to Z2 and back to Z1. So that is part C, Hamilton circuit. Maybe that's better. Maybe. Z1, Z3, Z7, Z8, then Z14, Z13, into the squarish thing, Z15, Z9, Z10, Z16, Z12. I've come back out to that bottom right corner, so I'm going up to Z11, into Z5, 6, 4, Z2, and then back to Z1 to finish. That should be a good Hamilton circuit over here. Part